All right. Today is the 28th, yes. To do these problems, we have to make the bases match. I'm not allowed to change the problem. I'm not allowed to change the value of any of these pieces, but I have to get the bases to match. Is there any other way of writing 5? Anything that has the same value but looks different than this? 5 with an exponent of 1, I can write it like that. Has the exact same value. Do these bases match right now? No. So I have to think of a way of rewriting this one so that it has the same meaning, it has the same value, but it looks different. 5 to the second power. Again, we can't divide these. 5 squared is the same as 25. So if I write 5 squared, it has the same value as the 25 right above it. But that 25 had an exponent on it. So my 5 squared needs to have an exponent on it. Do these bases match now? Yes. Why did we want the bases to match? That side, so the right-hand side is the bell work that you got yesterday. If you weren't here yesterday, grab that. Other than that, you also need the notes. I'm sorry, one more time, Precious. What were you saying? Yes, the exponents, when the bases match, the exponents are equal. We have to multiply this 2 and x together. So I have 2x equals that exponent of 1. What would I need to do to this now to get the x all alone? Divide by 2. So x equals 1 over 2. Or if you would prefer to write that in decimal form, you could write that as 0.5. Then I come over here to number 2. Is there a way that I could write 4 so that it looks different, but it has the same value? It's still equal to 4. 4 to the first power, or I could write what? 2 to the second power. So 2 to the second power. It had an exponent on it already of x. What about this guy over here? 1 over 32. What do you know about the exponent if it's 1 over something? Has to be a negative. So 1 over 32 is equal to 2 to what power? You said you know it has to be a negative power. Grab your calculators. Try some different numbers. 2 to the negative 5 power, yes. 1 over 32 is equal to 2 to the negative 5th. So I'm going to rewrite this side as 2 to the negative 5th. Do those bases match? Yes. Since the bases match, what can I do? Make the exponents equal. So here's the exponents on this side. We multiply those together. Here's the exponent on this side. So I get 2x equals negative 5. What would I do to solve that? Divide both sides by 2. So x is equal to negative 5 over 2. Or if you wanted to write that as a decimal, negative 2.5. All right, one more on the bell work. Is there a way to rewrite 3 so that it has the same value, but it looks different? That's how I rewrite 3. 3 to the first power. So 3 is 3 to the first power. Bring down that exponent of 6x. How would I rewrite 9? 3 to the, not third, 3 to the second. Remember, the exponent is how many times we multiply it by itself. So 3 to the second power. But then I've got all of this exponent here, 4x plus 2. What do I do with the exponents now that my bases match? Make them equal to each other. Here I'm multiplying 1 and 6x together. What is 1 times 6x? 6x equals, over here, I have 2 times everything on the outside. So I'm going to have to distribute that 2 to all the pieces on the outside. Distribute the 2 here. So I have 6x equals 8x plus 4. I need my x's on the same side if I'm going to solve for x. How do I get the x's to the same side? Minus 8x on both sides. Cancel that out. What is 6x minus 8x? Negative 2x equals 4. Divide both sides by negative 2, and x equals negative 2. Very nice work. All right. If you don't have a calculator, you are going to need one. Like in 5, 4, 3, 2, 1. We're going to use it like right away in the notes. Does anybody else not have a yellow calculator? So everybody should have the new notes packet from up at the front. Really big print at the top. It says notes. Down at the bottom of the page, it has what looks like a calculator screen. We're going to talk about common logarithms today. And I've brought this up already. We talked about it a little bit on Thursday. We talked about it a little bit yesterday. Base 10 logarithms are called common logarithms. They get used in a lot of different applications. Common logarithms are usually written without the little 10. So when you see just log, that is exactly the same as log with a little 10 there. Same exact meaning. So I want to fill in this table. If you see log 1 equals 0, that is exactly the same as log with a little 10, 1 equals 0. So what is the base on the common log again? The 10. There's the base. Which piece is the exponent? The 0. So what do we call the 1 there? The argument. If I rewrite that in exponential form, we write the base first, 10, to the power of my exponent equals my argument. So this would be equal to what over here? Equal to 1, equal to my argument. What's the base on this again? Base 10. Here's the argument now. And here's the exponent. The argument on this one is 10. But the base is also 10, right? So I would have 10 to the power of my exponent, which is 1, 10 to the first power equals 10.
So is that 10 from the base or from
The 10 that I wrote in purple is from the base. This 10 after the equal sign over here is the argument. When you see just LOG, it's a base of what? Base 10. Which piece is the exponent? The 2. So what's the argument? 100. So if I rewrite that in exponential form, base of 10 to the power of 2 equals 100. Very last one, base of 10 on LOG. The exponent is this m right here. This, all of this is my argument. Thank you. So how would I fill in that blank over there? 10 to the power of m equals my argument. The argument was also 10 to the power of m. Anytime you see just LOG, the base is 10. So we can rewrite it in its exponential form with a base of 10. All right. Now you're going to need your calculators. Do you have a button on the calculator that just says LOG? Yes. Yes, where is it? Right underneath that green second button. That is the common log. That is log base 10. This key is the common log. It has a base of 10. I want you guys to practice using that button. We're going to calculate the log of 8. So push that LOG button, log. It's going to automatically open up parentheses for you. I want you to put 8 in there. And then close the parentheses. And hit enter. So I'm going to write down all the things that you see on your screen. It's 0.9030. 89987. The directions here say to round it to the nearest 10,000th. That is 4 decimal places.
So 90, 30.
So I go over 4 decimal places, that would be chopping it off right here, right? I'm throwing all this out, but what do you notice about this number right here? Yep, this is 5 or bigger.
So that means it's 30. I mean, 90, 30.
Yes. When that number is 5 or bigger, we round up. Nope. But we are reviewing some basic rules of rounding because the SAT is coming up and I don't know that they won't take off points for rounding properly. So log of 8 is about 0.9031. Log base 10 is nice and easy just because we can pop it in our calculators. Let's flip the page and look at example number 2. Example number 2 is everybody's favorite. It's a story problem. This is actually how they calculate this. If you take a physics class, other science classes, this is the equation that they use to relate the magnitude of an earthquake to how much energy it releases. What variable are they using to mean the amount of energy? E. Energy, E. And what units are they using for E? Joules. What variable are they using for magnitude? M. This is Richter scale magnitude. They use M for that. Here is the equation that relates the amount of energy to the Richter scale magnitude. Log E equals 4.4 plus 1.5 m. What does the m mean again? Magnitude. This is on the Richter scale. What does the E mean again? Energy. In joules. This scale, the Richter scale, wasn't created until the 1930s, but earthquakes that happened before its invention have been estimated using the Richter scale. For example, an earthquake in Cyprus that happened in the year 1222 is estimated to have measured 7 on the Richter scale. We want to know how much energy was released. So what am I going to do with that 7? Where would I put the 7? Yes. We're going to sub this in for m into that equation. So I'm just going to start there. Common log E equals 4.4 plus 1.5 m. Put this entire side of the equation into your calculator. Oh, sorry, we're subbing in what for m? 7, my apologies. We're putting 7 in.
How do you put log E though?
You don't need to. I said put that whole side. We don't put log e in. $14.9. You don't need to put the log in, honey. You're just putting the 4.4 plus 1.5 times 7 in. The piece that I'm trying to find, that capital E, what part of the log is it? Is it the base? Is it the exponent? Is it the argument? We are trying to find the argument. What's the base when you see just log? Base 10. What does that mean this 14.9 is then? That's the exponent. Rewrite this in exponential form. What would this look like rewritten in exponential form? Does log go in exponential form? What do we start with? 10. We start with our base. 10 to the power of 14.9 equals E. Now, can you put this in your calculator? Yes. Ten to the power of 14.9. I got 7.943282347, and then it has this weird star. And 10 to the 14. We don't need to write all that, but we do need to figure out the parts that we should write. What do we call this notation? When it has that star and then 10 to a power at the end. Does anybody remember what this is called? You've probably seen it in a math class back in Algebra 1, but you've also hopefully seen it in another type of class. S. Talk about classes that you take that start with S. Science. This is scientific notation. Let's round this to 3 decimal places, but then we have to include the scientific notation. What this means, that 10 to the 14, is that that number is actually way bigger than 7. It means I have to take that decimal point and I've got to move it this way 14 times. That's how big, that's how much energy was released. It's tons of energy. So I would write down 7.943, and then instead of the star, we normally do a times symbol. 10 to the 14th joules. This energy is being measured in joules. All right. Example number 3. Where is the x in example number 3? The exponent. We want to find the exponent. Do you guys know off the top of your head 11 to some power equals 101? I don't know that one. How do we isolate exponents? Logarithmic form. So we are going to rewrite this in logarithmic form to isolate the exponent. Remember, this is the whole point of logarithms, to isolate exponents. So what would this look like in log form? Log base 11, yep. This is our base. What's the exponent? It's not my exponent. X is my exponent, but what comes next in logarithmic form? 101. This is our argument. And that would be equal to what? That's equal to x. So now I have my exponent isolated. Can I put this in my calculator? What buttons do we have for logs on the calculator? We have only the base 10. And this is base 10. Is this log base 10? No. We need a new tool to be able to evaluate this. We're going to come back to this. We have to learn our new tool, and then we need to come back. All right? Flip to the next page, because that's where we're going to get our new tool at. What we are going to learn to give us our new tool here is called the change of base formula. We will use this to change the base to base 10 so that we can use that LOG button. So in symbolic form, when we change the base, if I have log with some base b, and then we have the argument afterwards. Gentlemen, focus, or I'm moving you. It's going to turn it into a fraction when I change the base. Up in the numerator, I will have log of my new base and the original argument over log of the new base that we chose and then this will have b, the old base, as this argument. So as an example, I could take something like log base 7 of 18 and I can change it to the base that's on my calculator. What's the base on my calculator? 10. So log base 10 of what? What would go up on top as that argument? The original argument, so 18. Over log of my new base, so log base 10. What would the argument be down here? 7. New base is 10. So I can use the button on my calculator. Do I have tools now to be able to put that previous problem in my calculator? Let's go back and look at it. Oh, hold on. Grab what you need. Huh? The whole purpose of this, Dwayne, is so I can change. I can pick a new base. We're going to pick base 10 so that I can use that button on the calculator. We could pick any base we wanted to, but I like base 10 so I can use the calculator now. Does that make sense? All right, wrong way. So we're going to go back to this one. So the new tool is the change of base. All right, so we had log base 11 of 101 equals x. How can I rewrite this log so that I could put it into my calculator? Log 101 over log of 11 equals x. Grab your calculator. Use the fraction key on your calculator. Fraction key on the top, log 101. Close the parentheses or else the calculator will yell at you. Go down to the bottom. Log 11, close the parentheses. And hit enter. 1.9246. Yep. X is equal to 1.9246544746. How many places did they ask us to round to? Does anybody remember from the other page? 10,000 is how many places after the decimal? 4. 4 decimal places. All right, so I count over 1, 2, 3, 4. That would chop it off right here. I get to throw this out. Do I round up or no? Yes. This number right here is 5 or bigger. So we round up. So x is 1.9247. Let's try that change of base thing again. I want you guys to try it on your own. Go back and look at example 4.
I have a question.
Yes.
If they switch sides, like the 101 is on the bottom and the 11 is on top, does that make a difference?
Yes, it does. It would make an enormous difference in your final answer. So one of the ways I always remember this, when you think about singing, when you think about instruments, is a bass high or low? Low. Bass instruments, bass voices, those are low. Bass goes on the bottom. I want you guys to try change of bass on this example number 5 here. Use change of bass. I want you guys to practice writing it and practice putting it in the calculator.
Example 5?
Yep, example 5. There was no example 4, sorry.
You said we do this on our own?
Yep, I want you to do example 5 on your own.
Okay.
Yes, give me just 1 second. D-I-A-L-O. There you go. You're welcome. What's this going to look like when we use change of base?
Log 11 over log to 2.
Log 11 over log 2. When we put that in the calculator, 3.4594. What are the numbers after that?
It was 31619.
31619. Did I write that down right? Log 11 over log 2. 459431619. Yes. We're supposed to round this to how many places? Yep, nearest 10,000th. So 4 decimal places. So 1, 2, 3, 4. I chop it off here. Do I round up?
No.
No. Not 5 or bigger. Do not round up. So log base 2 of 11 is 3.4594. You okay? One last problem I want to do with you guys. We're going to call it a day. This also finishes up all of 7.3. 7.3 is short. We're going to do example 6. It's got a whole bunch of words, but it has how many formulas in it?
2, 1.
Just one formula. Yeah, there's a couple numbers in there, but there's only one formula. Just this right here.
I don't know. Who you thought I was? Go figure that out.
What does that equation represent? What does it tell us it represents?
The relationship between the amount of revenue gained from advertising and the amount of revenue received.
Ooh, which part of this means the amount of revenue received without advertising? Which part of this shows us how much money they'd make even if they didn't do any advertising at all? That variable X is the revenue that they would get without advertising. We need to find X. All right, so I'm going to recopy this equation down here. $325,000 equals X plus 44,000 log base 5 of 36. If I knew how big that was, couldn't I just subtract it from both sides to get X all by itself? Can I put that part in yellow in my calculator? What do I have to do so that I can put it in my calculator? Yep. Use change of base here so we can put this in our calculator.
So that's going to be log 36 over log 5.
Yep. So yeah, that would be log 36 over log 5. I'm going to pop that inside parentheses because what's in front of that? 44,000 everything else I'm just bringing straight down. Put this in your calculator. Round to the nearest cent. That's what it tells us right here. So I'm going to put 44,000 parentheses. Fraction log 36 over log 5, and then I'm going to hit enter.
97,968 and 88 cents.
What would I need to do now to get X all by itself? Yep, subtract that from both sides. So I'm going to subtract this 97,968 and 88 cents from both sides.
We won't have to do problems this big on the test, will we?
With numbers that big?
Yeah.
It is possible, but not likely. What do you get?
22,
Point what? We're going to round it to the nearest penny. 12. So if this company didn't do any advertising at all, they would still make $227,000 and some change.
I wouldn't be mad.
You wouldn't be mad? I wouldn't be mad either. That finishes up all of 8.3. That's all of 8.3. That was this entire notes packet. Tried to make sure you guys actually had enough room to write everything down this time. All right, so the 8.2 homework that was on paper, I passed that out last Thursday. That one is due today. That's the expanding and condensing homework. If you have that, you can pop it in the basket up here at the front. If you don't, bring it tomorrow. I'll still take it tomorrow. The homework over 8.3, over what we just did in this packet, is due on Thursday, and it is a McGraw-Hill homework. There is no paper for that one. What else happens Thursday? No coming to school. Does that mean you're not responsible for anything? Nope. On Thursday, the only way you guys don't get counted absent is if you log into Canvas and you do a thing. There will be a very, very short, I'm thinking 2-3 questions tops for this class. You need to get in there and answer those questions or you will be counted absent. It shouldn't take you any more than like 5 minutes. I'm not looking to tax anybody's brains. Thursday, do your e-learning stuff. Juniors, you're going to be taking the SAT all day long. Not all day, half the day. So it's very short, very sweet.